which is it's very similar if you've attended our meetups before. So welcome everyone to this 27th PyData Cambridge meetup. This is our January meetup, our first one of the year. And as has been for this past months, we are fully online. So the agenda today, we have one talk, and it's from Aliaksei Mikhailiuk. I hope I said that correctly. And it's about active learning, scaling, and dataset merging for ranking and rating surveys in image quality assessment. This is the only talk we will have today, and we are kind of trialing having only one talk instead of two. Maybe people prefer, since there is a little bit of Zoom fatigue. I know it myself. I get a bit tired after a whole day of Zoom meetings. So we're trialing one talk. Please let us know any feedback if you think this is a good idea and you rather have something like this. Great. Another reminder, this is being recorded and we are already recording. So who we are, so we're the local meetup chapter of Cambridge, UK, PyData Cambridge. We started in November 2018. We do monthly meetups every last Wednesday of the month, and it's organized by me, Federico, Joris, Leandro, and Ole. And just to remind you that we do this as volunteers. So just to remind you, this is a volunteering. Essentially, we are just volunteers. So yeah, we are supported by NumFOCUS, which supports PyData, which is really an educational program of NumFOCUS. So all the meetups, conferences that you might be familiar with, the YouTube channel, it's all thanks to NumFOCUS. NumFOCUS has a lot of projects that it supports, many open source projects. Many of them you might be using, like personally, using Pandas a lot, using Jupyter, Matplotlib, etc. And yeah, they support these projects that we all use and support this meetup itself too. So please consider donating to NumFOCUS. You can go donate all year. There's some donation drives, but you can always donate at any point. You can do a recurring donation at all types of things. So please consider doing that. We also like to remind you that in this meetup, we have a code of conduct, which is the PyData code of conduct. The general idea is that you have to behave professionally. This is a professional environment. So essentially no harassment, no sexist or racist or exclusionary jokes. And we have a response team for the code of conduct, which is all the organizers. So you can always contact us if you think there has been a breach of the code of conduct. And if you wouldn't rather contact someone that is not part of the organizers, but is a representative, a separate representative, independent representative of the response team, you can contact Leonie. We are always looking for more speakers to present in the 2021 agenda. And I think the donation drive to NumFOCUS is still open. That last point is already from a different meetup. I forgot to delete that. I'm sorry. But yeah, we're always looking for speakers. If you are having an interesting talk, an interesting topic, please email us or contact us, or just mention it in the message chat here in Zoom. We would also like to talk thanks to our sponsors, which is ARM, Fetch AI, NumFOCUS itself, and Raspberry Pi, which supported us when we were an in-person meetup. They supported us this whole time since we started. So we still consider them our sponsors, and hopefully we will remain with them. Our sponsors can support us with many things like Zoom licenses, meetup fees, etc. When we're in person, we can sponsor people traveling. Great. So from ARM, which is where I work and where Leandro works, two of our organizers, we have some positions, some data positions like principal data engineer, graduate data engineer, data analyst, and senior performance analysis engineer. Some of these positions are unfamiliar to me, but I'm always happy to discuss and talk about these positions. If you're interested in applying, we are hiring in a lot of other positions. So please do take a look. From Raspberry Pi, we just wanted to highlight that they have weekly live streams with educational activities. I think these are still ongoing about doing digital making at home. Please just check the Raspberry Pi website for any activities that they're up to. Our sponsor is Fetch AI. They have a lot of updates for us. They've built an applications framework to enable hotel operators to deploy autonomous AI travel agents to market. So you should really take a look at what Fetch AI is doing. You can also join their Discord if you'd like to have a discussion with them. And if you want to collaborate with them, you can contact them directly. Great. So I did say, if you are interested in speaking, please contact us. How can you do this? Well, you can contact us either Twitter or email, but we also post these recordings in the YouTube channel of PyData. We're always looking for sponsors, so we're always willing to discuss, and we're always looking for speakers. I will also highlight that please do feel free to introduce yourself in the Zoom chat. What you do, why did you end up in this meetup, anything that you would like to share. Maybe you'll find someone who's interested in the same things as you. And I'll stop now and let Aliaksei share his screen, and we'll get started.
Hi, everyone. Can you hear me?
Yep, we can hear you okay, and I can see the presentation, so I think we're good.
Perfect. So to start with, my name is Aliaksei, and today I'm going to talk about probably one of the major parts of my life in the past 10 years. This is my PhD, and I'll be discussing the topic of active learning, scaling, and dataset nurturing for ranking and rating surveys. I would mostly concentrate on the examples in image quality assessment, but bear in mind throughout the whole presentation that those techniques that I will be discussing today are applicable to many, many problems, as you'll see also during the presentation. So first of all, a little bit about myself. I'm currently a research assistant at the Department of Computer Science at Cambridge University. As I mentioned, I've just finished my PhD under the supervision of Dr. Rafal Mantiuk. And before that, I was working with deep learning algorithms for multidimensional data reconstruction, also at Cambridge, under the supervision of Dr. Anita Fall. I was happy to see her in the audience today. I also worked on machine learning and computer vision for pothole detection at Bristol under supervision of Dr. Naim Danoun. So to start off the presentation, let's look at slightly bigger picture. There are very many applications in image processing that require some sort of fine-tuning. So that would be super resolution, colorization, and denoising. Those applications are very common to every one of us. When we are using our smartphones, there are many different processing stages that camera hardware is performing, and also many post-processing stages in the software. And to develop all those algorithms, we need some sort of tuning. So we need to know whether images look good or not. So as I mentioned, it would be nice to have fine-tuning for those algorithms. But unfortunately, on many occasions, standard metrics that we are used to, such as PSNR, peak signal to noise ratio, are failing. So in this case, PSNR is greater for the left image and much lower, not much lower, but lower for the right image. Although perceptually, the right image looks much better, at least to me. So we need something different. The ultimate consumer of the digital content of images is the human, and thus we need the results to be perceptually pleasing for him. But at the same time, we cannot really use humans to fine-tune those algorithms directly, because it's simply inefficient to put a human in front of a screen and ask them to adjust the parameters of the algorithm until he or she finds the perfection. So it would be nice to find the model of human judgments for image quality so that we can use automated algorithms to fine-tune those image processing algorithms. But we run into the same problem. To fine-tune those models, we need human judgments, and collecting those is very expensive. As I said, it would be pretty difficult to put humans in front of a screen and ask them to compare or get the notion of their quality judgment simply because it's very expensive and time consuming as well. So for that, we need methods that would facilitate this process of collecting human judgments. Let's sidestep again and look at the full pipeline for image and video processing, and then I'll discuss every step in more details. So we start with the criteria. That would be either quality of the image, something that we would be judging, or aesthetic of the image. For example, if we're thinking about Photoshop, we need to have an image that is aesthetically pleasing, might not be of the best quality. We can also look at the visibility of the distortions in the image, or realism if you are talking about generative adversarial networks or generative models in general. Would be nice to have them produce images that are realistic enough. We then look into subjective image quality. So how to elicit those human judgments according to the criteria that we've selected before. Would it be quality of images, aesthetics, or visibility? Generally, two types of experiments are distinguished: ranking and rating. We then use the scores that we collect in those subjective experiments to fine-tune objective image quality metrics. As I mentioned, those automated models that model human judgments. And after that, we can use the feedback from those models to fine-tune image processing algorithms. So let's talk a little bit about different criteria that we've seen just now. First of all, we can think about aesthetics of the image. So we need algorithms to produce images that are aesthetically pleasing. And we would be thinking about the image at the top and the bottom, and whether the top one or the bottom one is more aesthetically pleasing. For example, for my subjective judgments, I very much like the noisy image at the top, simply because it has some atmosphere in it. But from the side of quality, it's probably not the best option. We can then look at the quality assessment, a different criteria. Here we would be judging the quality of the test image, which is on the right, with respect to the reference image, which is on the left. And clearly here, the test image is visibly worse than the reference image. Finally, if we're talking again about quality, visibility, and aesthetics assessment of images, the last criteria is visibility, where we want to figure out what parts of the image have noticeable artifacts in them. And here, for example, human observer might choose areas somewhere in the lake or at the bushes, pointing to them, saying that those are areas for which algorithm has not produced a good job. So, as I mentioned, today in the presentation, I will be mostly concentrating on image quality assessment. How do those data sets that contain human judgments for image quality assessment look like? And this is a perfect example of that for you in the slide. Usually there would be images that would be mapped to the quality score that is collected from human observers. And here, for example, you can see the reference image that is completely perfect, and then images decrease in their quality, as we can see by the quality scores that are obtained from human observers. And then image quality assessment models, objective image quality assessment models, automated models, would take an image as an input and try to reproduce the subjective score obtained from the human observer. I will talk about those models in more details later in the presentation. I should stop here for a bit and sidestep from image quality assessment and mention that the method that I will be listing further in the presentation are very applicable to many problems, not only image quality assessment. So we're talking here about scale inference, how to infer the scale of the quality for images, in my case, or for example, many other applications, such as education. For example, last year we had a massive problem with GCSE results, where we had to map somehow the performance of the students across different schools so that they can get to university. And this is also the problem of scale inference. We can also think about customer satisfaction, how to infer the scale for products such as headphones, or similarly sports games, where we want to have players that, the ranking tables of the players, such as chess or tennis tournaments. We can also think about the scale for realism, as I mentioned, generative models, or image quality assessment, something that I'm returning back now. So how to elicit human judgments? This is the general question that is being addressed in scale inference. So there are two different methods. One method is rating, where we ask observers to rate images on a scale, either continuous or discrete. So here, for example, we can ask how good is in the first case, how good is the image on the scale from 1 to 100? Or similarly, on the second example, we can ask them to put the image in one of the categories. Another kind of experiments that we can use to elicit human judgments is comparative judgment or previous comparisons. Similarly, they can be called ranking. So here there are many different examples of how we can elicit this ranking or comparative judgment. We can either compare images side by side, or ask observers to order them in the order of quality, or cluster them together, so put similar in quality images together. I should stop here and mention that for rating, it's pretty straightforward to obtain the quality score corresponding to the image. If you think about it, if we ask 10 or 15 observers to rate a single image, then we can easily say that mean observer score is just the average of the scores. And then we can also find the uncertainty in the observer's judgment by finding the standard deviation of the observer judgments that we elicit for this image. We can then do some post-processing to remove observer bias, but still the process is pretty straightforward. The bigger question is, how can we map the previous comparisons, so those discrete judgments about image quality, to one-dimensional scale? And this is something that I'm going to talk about now. So how can we scale previous comparisons? First thing, I will talk here about the most general model that is usually used for scaling previous comparisons, that is commonly used by Microsoft in TrueScale or in many economics studies. This model is also called Thurston model. So for that, we model quality scores as normal distributions with mean and standard deviation. In the most simple case, we have a fixed standard deviation for all scores. Now, probably question to all of you is, how can we map those previous comparisons that we collect, so the binary outputs of one condition or image being selected over another image, to the probability of one being better inferred from the quality scores? So give you just a second here before I give an answer. And simple thing to do is to find the difference between the two. And luckily enough, since we're working with normal distributions, the result also will be normal distribution. What we can do then is to find the area under the curve from -infinity to 0, and that would give us the probability of condition B selected over A. So what part of the distribution is on the negative side? That is the probability of condition B being selected over A. This is essentially the definition of the cumulative distribution function. Once we know that, we can then use some modeling to infer the quality scores. And here we are working with the binomial distribution, where we have several parameters. So first of all, we are obtaining the product across all pairs of conditions. We have the probability of the outcome inferred from the quality scores that we are trying to model. And this is all very nicely fits in the binomial distribution, because we putting that into the power of number of times one condition was selected over another condition. And then we can use maximum likelihood estimation to infer the scores. This is a very simple model that gives us point estimates. There are more complex models, as we see further down the presentation, that include Bayesian estimation of the scores, where we can infer the whole posterior. So one of the things that I should mention here is that it's very well known that ranking experiments are much more accurate than rating experiments. But as we saw with the previous slide, we have to do this product across all pairs of conditions. So the drawback here is that for n conditions, there are very many possible pairings. So how do we select those pairs of conditions that bring the most information to the scale? This is the question that we're trying to answer now. So how can we minimize this number of comparisons performed while maximizing the information about the scale? Generally, there are two types of methods that are distinguished: sorting-based These are based on a simple heuristic that similar in quality or skill pairs conditions should be compared to each other. So images of similar quality should be paired with each other because it will bring us more information than comparing images that are far away from each other in the scale, because comparing very poor quality image to very good quality image doesn't make sense because the outcome is obvious. It's much more interesting to compare images that have very close quality scores. Another type of methods is based on models, and those are information based. And here we are actually selecting the pairs of conditions that would be minimizing the uncertainty in the scale according to some information gain criteria. And in my PhD, I worked on the method called ASAP, which has recently been presented at the ICPR conference, for which we received the best paper award. So please feel free to check out the code and the project page. That might be useful for your work as well. So now I'll describe typical pipeline for information gain based methods, to which the method that I have developed also falls. So we start from pairwise comparisons. This would be data collected so far. We then infer the scale. Those would be usually the scale inferred with the full posterior distribution instead of likelihood estimation. We then use the scale to select the next comparison. And here we're using those information gain metrics that would choose the next pair of comparisons to perform. Then we run the experiment. That would be either a game or a chess tournament or image quality assessment experiment with a human observer. And then we update the data collected so far. So how can we infer the full posterior? And in my method, we are using TrueScale, where we are interested in inferring the score variable, normally distributed. Given the output variables, those would be the outcome of the pairwise comparison. Very nice thing is that we can actually not approximate the posterior as many methods do that work with information gain criteria, but infer full posterior, gaining as much accuracy as possible about the inferred scores. As I mentioned, it provides the distribution of the scores, both mean and variance. For inference, we are using sum product algorithm with expectation propagation via moment matching. And this is used because the binary outcome variables are not conjugate, likelihood from the binary output variables is not conjugate to normal priors. So we need some iterations. For more details, please check out the TrueScale paper. So now we are having this scale, can use expected information gain to infer the next possible pair of comparisons. So we start with the data collected so far. Here is the matrix of pairwise comparisons, where in each row and column we have a number, and this number is the number of times the condition in the corresponding row was selected over condition in the corresponding column. So if we look at the conditions 2 and 3, condition 3 was selected 1 time over condition 2, and condition 2 was selected 3 times over condition 3. We now simulate all possible comparison outcomes and infer the scale for all possible simulated comparison outcomes. After that, we compare the inferred scales for all simulated outcomes with the original scale. In my case, I'm using KL divergence. And then we can also obtain the expected information gain by weighting by the probability of the comparison outcome. Let's look at the example. So we have this pairwise comparison matrix. In the plot on the right, we have the inferred scale. First of all, what we do, we simulate the outcome in which condition black won blue. We calculate the KL divergence with the original scale and the probability of the result. Probability of the result is simply the, as we saw with the maximum likelihood estimation, is the cumulative distribution function of the difference between two variables. We then go back to the original scale, simulate the outcome for blue won black, find the KL divergence, also find the probability of the results. In this case, the probability of the result for blue winning black is higher, as we can see, obviously because it's better. And then we can find expected information gain with this by weighting the outcome with the probability of the outcome, by weighting KL divergence with the probability of the outcome. So talking about the results, I should mention that in this graph, RMSE denotes the accuracy of the method. So the lower RMSE, the more accurate the method is, and standard trial on the x-axis is the number of comparisons performed so far. There are three distinct classes of methods, and as you can see, the sorting-based methods perform the worst. So I've shown you the two different categories of methods that can be used. Then we have information gain-based methods that use approximate scale inference. And ASAP follows with the full posterior update based on the true scale with the highest accuracy. So in our work, we've figured out that it's very important to infer the most accurate scale distribution to attain the highest accuracy for active sampling of pairwise comparisons. So if you look at the code is very simple. We start with the pairwise comparison matrix. Then we initialize the algorithm. This code is, I should mention, is on the GitHub, so please feel free to check it out. And then what we do is just run ASAP with the pairwise comparison matrix and get the pairs to compare. If you are interested in this work, please feel free to check out the paper. Saying all that and working on this method ASAP during my PhD, I was thinking whether it can be possible to reuse the data that has been collected so far from other experiments. So there are many different data sets with image quality that are available that were collected before me. So we might not even need this active sampling method to compare, to select, to collect new data set. We can just maybe reuse the data has been collected so far. So it would be nice to start with two data sets. One data set has images with respect to their quality, and another data set has images with respect to their quality. Can we just somehow merge this data together so that we have larger data set with image quality, and then we can train more complex models on that larger data set? The short answer to that is actually we cannot. And one of the problems here is that different scales and different experimental procedures prevent from direct merging. So one data set can be coming from pairwise comparisons, another data set can be coming from rating, and how can we actually merge them together? Those have different scales. One has from, for example, 0 to 10, another one from 0 to 100. How can we find the correspondence of 10? Is it 100 in a different scale? Or so this was the question that I was trying to address in this work. How can we merge them together so that we maybe do as few measurements as possible? So one thing that occurred clearly to me that to merge those data sets, it would be nice to find those correspondences between the highest scores, lower scores, and how those data sets are aligned together. And I figured out that it would be very difficult to get away without any new measurements performed on the data sets. So we would need to run some experiments to infer the relative position of the scales. As I mentioned, this is also the work that is related to my PhD. Please feel free to check out the paper and the code. I think the QR code leads you to the project webpage, so please feel free to scan it. So coming back to the problem, we have two data sets. In the top left corner, we have a data set that was collected from pairwise comparisons. So it has pairwise comparisons, which is obvious. Another data set is obtained with the rating experiment, data set 2. Those are, as we remember, distinct human judgments about the quality of every image. One thing that was necessary, that I figured out was necessary, is to find the relative difference in the rating scores compared to pairwise comparison outcomes. So one thing that I had to perform for rating data sets that I was merging with pairwise comparison experiments is to introduce pairwise comparisons to rating data set as well. After that, I also introduced the cross data set comparisons to align the scales together. With all that, I used the maximum likelihood estimation procedure to merge the scores together. So as a visual example, we have a dataset score on the y-axis. Let's pretend that we don't have x-axis and we have only the axis to the y-axis, the original dataset score. Those datasets are obtained from rating experiments. What we do is we introduce the pairwise comparisons within the dataset, and we also introduce the pairwise comparisons across the datasets. After we have those pairwise comparisons, we can scale the data with the procedure that I will explain in the next slide to obtain the true quality that is on the x-axis, so aligning the datasets together. So we need to do some modeling here to ensure that we have the joint model for both rating and ranking scores. So first thing is to assume some relationship between the ground truth scores that we saw on the x-axis in the previous slide and the y-axis, the original rating score. And in my work, I use a very simple linear relationship. So here we have, we assume that the rating experiment scores are normally distributed, and they can be mapped to the ground truth quality score QI with a simple linear relationship with A and B. And this is actually not such a poor assumption, given that we need to have monotonic relationship between the rating scores that we obtain and underlying ground truth score that we're trying to infer. So the increase in rating score should be reflected in the increase in the ground truth score that we're trying to infer. What we do then, we can obtain the probability for all rating scores by multiplying across all observers and across all conditions in the data set. For pairwise comparison, we assume the model that was used in the previous example based on the binomial distribution. Then we can use the full model, which would be just the product of the pairwise comparison model with the rating model, and then we also multiply by prior to ensure that the quality scores are bounded together, not spreading out too much in the scale. As I've mentioned, since we introduced those pairwise comparisons across the data sets and within the data sets with ranking, we actually link all the probability models together. So talking about the code, we start with the pairwise comparison matrix. Those would be pairwise comparisons that are collected for different data sets. So for example, in this data set, in this example, we would have data sets with 2 different sizes having 4 images and 5 images respectively. We would have entries in the pairwise comparison matrix in red and blue corresponding to 2 different data sets. Those would be the comparisons within the data set. And we would have also comparisons across the data sets in black here. In mean opinion score, we would have also different sections for different data sets. We would have in red rating scores collected for each individual condition for the first data set, and in blue for a different data set. As you can notice, in the blue data set, we have 1 row missing. But this is not a problem because we have collected pairwise comparison for the missing condition in the pairwise comparison matrix. So we can actually infer the underlying quality score for this condition from the data that we have overall from both pairwise comparison and rating. We then use a simple method that is included in the GitHub repository, merge data sets, provide the pairwise comparisons, mean opinion scores, and data set sizes, and we infer the parameters that we have in our model. So having all this data that we have collected either with active sampling algorithms that we have developed or by merging multiple data sets together, having a plethora of images versus their subjective quality scores, we can train objective quality metrics. So train some model to predict the quality score from the image. So there are several methods that can be used for that. First one is based on natural scene statistics. Another one is based on modeling human visual system. And finally, we also have a class of methods based on deep learning that use automated feature extraction to regress to the quality score. So first of all, natural scene statistics, those answers ask a simple question. What do natural images, so undistorted, clean from noise images, have in common that is destroyed by noise? Those are usually based on wavelet decomposition, as we see how it works in the next slide. Once we have the wavelet decomposition of the image, we can use the coefficient of this decomposition as features, which we then use to regress to the quality score. Those usually do not need any reference image, so we can just pass a test image to those natural scene statistic-based image quality models that would give us the quality score. This is to contrast it with the full reference methods that would need also the undistorted image reference image passed with the test image, and we would find the distance between the two, as I'll show for different class of methods. So what we have here is wavelet decomposition. Those are simple basis function, and we actually can decompose images into different kinds of wavelets, and probably the simplest example that everyone encountered in school or in early years of the universities, Fourier decomposition. Those would be simple decomposition to the cosine and sine basis functions. Once we decompose the image into those, we can use the coefficients, as I mentioned, as features. So here, for example, we would be decomposing an image at different scales. Wavelet coefficients are features. We often use those methods, use natural statistics methods, use PCA to reduce the dimensionality because there are many coefficients. Not all of them are useful. Once we perform the PCA, we can then regress to the score. Many methods use either SVMs or perceptrons to regress to the quality score. So here we have three images. Original image undistorted by noise, image with white noise, and blurry image. Then we can see the coefficients for one band of the wavelets, and we can clearly see that those have very different distributions. So there can be actually something that we can find to regress to the quality score. Another kind of methods is based on modeling human visual system. Those ask a question: can we use model early stages of human vision to figure out what human eye picks up as something undistorted in the image? How can we distinguish with our early stage vision as having some distortions or not having distortions? So those are usually white box models. Two very good examples of those models are HDR-VDP, a very popular metric, and FSIM, also very popular method. Usually, as I've mentioned, to contrast it to the natural scene statistic-based methods, these are full reference where we are supplying both the test image and reference image to the metric, and then find some discrepancy between the two. So one of the things that we can use is the contrast sensitivity function. Not sure if many of you are familiar with that, but it is a function that tells us whether we can see the variations in the frequency under different contrast. And generally, humans have this curve shown on the left, where some variations are more visible for the lower spatial frequency, and some variations are less visible under different contrast. We can then include that information that some of the frequencies will be masked, given some contrast in the quality metric, so that we can omit some parts of the image where the contrast is masked. This is a simple example where we feed reference signal and distorted signal, do some preprocessing, CSF filtering, contrast sensitivity function filtering, where we, as I mentioned, we mask parts of the signal and do not take it into account when we are computing the quality score. And then can do some post-processing stages to get the final quality score. There is final class of method that is based on deep learning. Those are usually black box models, often end-to-end trained, but unlike other methods that I've described, they need a lot of data to be trained. And this is actually one of the biggest problems in image quality assessment. As I mentioned, collecting this data is very expensive, since we cannot we can, but it's very time consuming for a human to sit in front of the screen and press one or another for one image being better than another. So those are just gaining popularity when we are starting to see much larger data sets in image quality assessment. They usually use standard CNNs, convolutional neural networks, as the base, usually pre-trained, and then fine-tuned for image quality assessment tasks. So having all that, let's see how they compare to each other. I test all metrics that you will show the performance of on the TID 2013 dataset. It was one of the largest datasets when I started my PhD 3 years ago. It contains 3,000 images with their corresponding human observer judgments. I use Spearman-Frank order correlation coefficient to report the accuracy of the compared methods. Generally, the higher coefficient, the better. And I should also mention here that no reference metrics were not tested on all the data set, but only on the specific distortions, because as we've seen, we need to, or we have to, with current methods, to be very specific to distortions that we are trying to address with those natural scene statistics, because different distortions introduce change the composition coefficients differently. So what we can see here are the performance results. Blue are full reference metrics. Those are deep learning based, and those based on modeling human visual system to some extent, tested on the full data set. And there is also a subset given in red. Those are no reference methods tested on the subset of distortions. And as we can see, deep learning based methods actually attain the best performance, even though many of them are trained with quite small data sets. So having all those metrics, where can they be used? We're coming back to the first slide of my presentation. We can use it for performance evaluation of image processing methods. So those that would be either denoising, deblurring, super resolving the image. We can also use it as an objective, as a loss function for image processing algorithms, either as end-to-end loss, if it's differentiable, or as a feature extractor. Or similarly, it's very common now to use it as a regularization for generative model training, because essentially we want the produced results to be also perceptually pleasing, not only realistic. So with all that, I would like to wrap up my presentation. Thank you very much for your attention. For further links and questions, please feel free to message me. I have GitHub repository that is mine. We also have Rainbow Group GitHub repository that is for the Cambridge University Rainbow Group at the computer lab. So there is quite a lot of useful code pieces there as well. There is my email and also Medium account. I try to publish regularly there as well. Thank you very much. Are there any questions, or is there any in this format of discussion?
Yeah, let's see if there's any questions. I do have one to start us off. Are there any, let's say, is there any plans on collecting more data, since the deep learning methods seem to be quite well performing? I'm assuming the more data they get, the better they will get. Is there any anything planned to collect more data of this type?
Definitely not by me, but there are many works that are evolving. Were evolving in the past few years, maybe 2 years, that were addressing larger and larger scale data sets. So the data set that I have shown the performance of quality metrics TID 2013 had only 3,000 images. Now we have data sets with 10,000 images. Those are usually collected with Amazon Mechanical Turk. But again, thinking about the cost, it's very costly to collect this data there as well. So methods that I've described here are also useful for collecting the data, large data sets there as well. So I think that the problem is being addressed, but gradually.
Yeah, cool. Yeah, are there any other questions? Please write them in the Q&A window.
Yeah, I think I can go one more while people type their questions.
Yep, go ahead.
Okay, so I noticed that your examples were mostly with kind of photos or kind of pictures like that. So how do you think the results you got here can kind of be transferred to other types of images that have different kind of, I assume, features, like paintings, for example, or drawings and stuff like that? Do you think they would generalize enough to capture the particularities of different classes of images?
I would say no. If you mean the image quality assessment methods, that
yes.
So those are mostly used for natural images. So for paintings, I would imagine there would be needed some aesthetics measurement that would tell whether a painting is aesthetically pleasing or not. So those methods that I have mentioned, they are not very good on those kind of tasks. Those are for impairment assessment. So how much is the image distorted by different kinds of noise?
Oh, I see. Yep. Thanks.
Okay. So yeah, last chance to get some questions in before we finish. And thank Aliaksei. There's a question in the Q&A. Here, I'll read it out. Here you talk about people ranking the quality of whole images, but I am wondering if similar methods could be applied to detection tasks. For example, in crowdsourcing applications when people tag features in a dataset, but the labels may vary depending on their subjective interpretation.
So those kind of methods that I described here, those are not addressing this issue, but there are very many methods that take that into account, including observer, how reliable are observers or participants of the experiment. But to answer this question shortly, the method that I presented here, they do not address that, but there are many other methods that do address that. And if you're interested, please email me. I have a bunch of papers to share with you.
Cool, thank you. So right, any other questions? One more. Why do we use wavelet transform while we can use the image using any transform?
That's a very good question. So essentially, there were many works that attempted different combinations. So if you're talking about any different transform, I'm not quite sure what the question is referring to, but different kinds of wavelets have been tried on this image example. For example, good decomposition would be Gabor decomposition, which is known to be naturally inspired, where we have those very similar Gabor wavelet decomposition going on in the brain when we are looking at the images. So there is actually quite a lot of research into how efficiently we can decompose the image with different basis function or different transforms to elicit those statistics. If that answers the question.
Yeah, we'll see. Yeah, another question. Yeah, so Krish, who asked the last question, says thanks a lot. Another question, just a question on the human judgments. What sort of background did these participants have?
That's a very good question. Generally, in the experiments that I have conducted myself, those would be my PhD peers, PhD students that would be studying with me. But if we're talking about Amazon Mechanical Turk collected data sets, the observers can have very different backgrounds. If we're talking about much larger data sets with image quality, then there is very little control, as we know with Amazon Mechanical Turk, about who is looking at the images.
Great. I say we can have maybe a couple more questions if there's still more. I'll wait for a few seconds. Okay, I think we don't have any more questions. So thank you, Aliaksei. This was a great talk, and hopefully you found the questions and interaction interesting. We'll be posting this video very soon on the YouTube channel, so you can share it with any of your colleagues, friends, and please promote PyData Cambridge. Thanks, Aliaksei.
Thank you very much.
Thank you, everyone.